Hey, my name is Danny, and this is my presentation on the arms race between fungi, bacteria, and human beings. It's very interesting stuff. So we're going to do it with penicillin. That's how we start. It was developed in a fungus originally, and it was used as an antibacterial to prevent infection. And it was discovered by Alexander Fleming on accident when fungi crept into his petri dish and reduced cell growth. And he's like, something here that we could use. All right, why did it evolve? Well, the ability for the fungi to synthesize penicillin confers resistance from bacterial infection. So this is just natural selection at play. Others who don't produce it die. So it's selected for. How does penicillin work? Okay, the beta-lactam ring, this butte right here. It works by inhibiting an enzyme involved in cell wall synthesis. Transpeptidase has a serine residue, and it nucleophilically attacks this beta-lactam ring and basically inactivates it. I'm sorry, the beta-lactam ring inactivates the transpeptidase. Sometimes the transpeptidase unbinds, but it has strong binding affinity. So it prevents cell wall synthesis. And then whenever the contents of the cell leak out, then the cell dies. All right. The benefits of penicillin. I mean, in World War I, it was expected that sickness was going to be the major cause of death. And that's always the case in many wars. And in World War II, when penicillin was systemically distributed to the soldiers and to the population, the death toll from pneumonia was less than 1% compared to the 18% in World War I. And it's estimated that, estimated that it saved 200 million lives since its production in the 1940s. All right, how did bacteria counteract us? So this is the arms race right here. Bacteria developed beta-lactamase, or should I say evolved. What beta-lactamase does is it comes in and it breaks the lactam ring. And then it just leaves after it breaks the ring. So it could break a bunch of penicillin, destroy it. And so therefore penicillin's useless. The bacteria outsmarted us, basically. And that's the start of resistance. So natural selection at play again. They started popping up right after systemic administration of penicillin, and in people and in agriculture and animals and such, and it instantly just selects against defenseless bacteria. And what you get left, as represented by this diagram here, is just a population of just resistant bacteria. All the non-resistant ones died, So how could penicillinases have evolved without humans as the natural pressure? Well, the genus Penicillium is one of the most common in the world. So if a bacterial species can will fill that niche of, preying on that fungi when no other species could, then they're at an advantage because they have an ample resource for food and space, to grow on and flourish. So much less competition. As you see, look at this crowded table. You're not going to get as much food as if you have this whole charcuterie board to yourself. And that's like the genus right here. How did people counter penicillin-resistant bacteria? Well, scientists put in the work and we figured out we could make amoxicillin and clavulanic acid, combine those together, and we have a very potent antibiotic. Clavulanic acid functions to inhibit beta-lactamase by covalently bonding to its active site and permanently inhibits it. Amoxicillin is the same thing as penicillin for the most part, except it has a broader range and so more broad spectrum antibiotic. It shares the same beta-lactam ring and thiazolidine ring structure. The only thing different is the side chain. And so here are the differences right there. And there's a bunch of varieties. Methicillin is going to come up. Here we go. How did we counter penicillin-resistant bacteria? So we made that, and then we also made methicillin. So 2 methoxy groups were placed on the benzyl group. So this is the benzyl group. We placed 2 methoxy groups right there. And so that prevents nucleophilic attack on this carbon by the beta lactamase. So, which is perfect. That's what we want. But we were winning, and evolution will catch up eventually with MRSA, or MRSA, methicillin-resistant Staphylococcus aureus. It's a strain that developed resistance against methicillin via more mechanisms than just hydrolyzing the beta-lactam ring. So, of course, they have a modified beta-lactamase that can hydrolyze it. That's how evolution works. That always happens. The interesting part is they have modified penicillin binding proteins. So anything involved in the cell wall synthesis, like transpeptidase and the likes, without getting into too many enzymes in this presentation. So their PPBs not only have less binding affinities, they also have higher rates of release after interacting with the antibiotic. Okay, here's the important one. And here's a beautiful example of evolution, in my opinion, is PBP2A. The interesting part about this is that it was encoded by a foreign DNA, Staphylococcus sciuri, and it was somehow horizontally transferred into the Staphylococcus aureus. And so that's just a beautiful example of how, they're not really certain of how this happened. It could be conjugation, transformation, who knows? It could be transduction. But evolution has many routes. It has many tools that it can use to continue and progress. And it's just, I think this is a beautiful example. PBP2A has a lower binding affinity for beta-lactam antibiotics and a higher transpeptidase activity. So remember, these PBP enzymes are involved in cell wall synthesis. So it's also an enzyme involved in transpeptidase. There's also transglycosylase and all this stuff, but let's focus on the evolution. All right, in summary, Penicillium chrysogenum evolved penicillin to defend against a pathogen. A pathogenic bacteria specifically. Humans discovered this defense mechanism and utilized it to cure our own bacterial infections. We're pretty smart. Many bacteria evolved beta lactamases to counter the defenses of fungi and people. So now they're resistant, and fungi can no longer protect themselves. People got to think of smarter ideas. So we synthesized and modified antibiotics, amoxicillin, clavulanic acid, methicillin, to counter penicillin-resistant bacteria. Well, bacteria evolved better mechanisms to avoid penicillin without even relying to destroy beta-lactam ring. So now we got to think of ways to destroy their counter defenses. And then they're going to counter our counter, and we're going to have to counter their counter, which is great. This is evolution. It's not too great. It's a fight. It's a process, but it's the world we live in. I hope you enjoyed this presentation. Have a great day.